Hey everyone, my name is Tovio. This is Galvanize Study Hall. Um, we're going to start off with a couple questions. There's a question from our Discrete PMF lesson. Question 1. Given a group of 5 potential blood donors, 2 donors are known to be universal donors. They have O+ typed blood. 5 blood samples, 1 from each individual, have been taken, and the blood type will be tested in random order until the first universal donor is found. Let the random variable x represent the number of typings necessary to identify a universal donor. So first find the PMF for the random variable x, then calculate the probability that it will take fewer than 3 blood draws to encounter the first universal donor. Okay, so when we're thinking about this, what is the probability of x is one draw, where we get a universal donor. There are 2 donors out of 5, right? And let's see, 5. Yeah. Let's say there are 2 donors out of 5. So the probability of getting an O+ donor on the first pick is just 2 over 5, right? And when we're thinking about building this, the probability of getting, of it taking fewer than 3 blood draws, what we're saying is draw 1, should be a 1, plus draw 2. And so we know what draw 1 is. That's going to be 2/5, right? And then draw 2 is a little trickier to think about. Probability of x is 2. So what we want to consider is that we don't want to get a universal donor on the first draw, right? And so we want to think about the complement of getting a universal donor, which is 3/5, right? There are 3 non-O+ typed. And then what is the probability of, we just want to multiply this with the probability of getting a universal donor, which is not 2/5 here, it's 2 out of 4, right? Because 1 has already been drawn on the first draw. So this is going to be our probability that we get a donor on the second draw. Let's just, so this is going to be plus 3/5 times 2/4, and we can just copy this. I'll just print it out and see what we get. Hmm. 0.7. So hope that makes sense. And that is the correct answer. And there's a fairly detailed explanation once you run it. But essentially, you're just building this with the probability that you get on the first draw plus the probability of getting on the second draw. And the probability of the second draw, you have to figure in the probability of not getting it on the first draw, which is 3 out of 5, right? And then you multiply that by the probability of getting 2 out of 4, which is what would be remaining from the blood draws. Like there's only 4 options left after you draw from the 5 options, and 2 of those need to be O+ type. So hope that makes sense. And let's look at another question. Geometric CDF example 2. Okay. All right. Okay, so we have to look at example 1 to understand example 2. Let the random variable x represent the outcome of a random experiment consisting of sequential rolls of a fair six-sided die. A successful roll of the die is defined as rolling the die resulting in 6 pips, showing. A pip is the name of a dot on the die, so that's going to be a probability of 1 out of 6, right? So probability of x equaling 6 is 1 out of 6. What is the probability that the first roll resulting in a 6 will occur on the 10th roll? So we can just plug these into the binomial PMF, and 1 minus 1/6 to the 10 minus 1 times 1 over 6 equals 0.0323. So 3.23% is the probability of getting the first roll of a 6 on the 10th roll. So in terms of the CDF, given the same random experiment, find the probability that the first die roll resulting in 6 pips showing will occur on or before the 4th die roll. So we can do this in a couple ways. One way is we can say so we're, well, one sec here. Okay, yeah. All right. So there are two forms of the geometric PMF, and in this form, K represents the first success, right? The trial in which the first success is encountered. And so K can't equal 0. And what we want to figure out here, if we use the PMF, we can say the probability that, let's see, the probability that K is equal to 1, right? We can do this in a couple ways. Why don't I just write this function really quick? So this is going to be, I'll just call it geom, and we're going to put in a K and a P, and we'll do just return 1 minus P to the K minus 1, and that's going to be multiplied by P. That should be exponents. All right, so this is the geometric PMF. And if we want to find out the probability of getting a 6 on or before the 4th die roll, we can do this a couple ways. We can do the geometric PMF where K is 1 and the probability is 1 over 6, right? And we can multiply or add that to K is 2, K is 3, and K is 4. And believe this should get us the right answer. So yeah, 0.517, 0.518. Now we could just apply the geometric CDF, right? We could say def geom CDF and KP, and here we've got 1 minus 1 minus P to the K, right? So this is, we can just say 1 minus 1 minus P to the K, okay? And this is going to be a little less code. We can just do print, and then K is going to be 4, and P is going to be 1 over 6. Oh. Yeah. And notice that gets us the same answer. Slightly different because of rounding error way out here on the right, but these are the same, effectively the same. So yeah, hope that clarified where your confusion was. Let me know if there's still some confusion there. Challenge 6 in the iterations problems. Okay. Let's take a look. So challenge 6 in our practice problems for iteration. Why? Let me just jump back to this geometric distribution. There's a question, why do I subtract by 4? I'm not seeing any subtraction by 4. I'm not entirely sure what you're referring to there. Yeah, we don't subtract it by 4 at any point. We do look at the probability for oh, y is k 4. Okay, this is probably a confusion related to which version of the geometric PMF and CDF you're using. So if you're using the geometric PMF that is inclusive of the success, the first success, then you include 4, right? You include 1, 2, 3, and 4. If you're talking about the geometric PMF that excludes the first success, then we would do probability of 0, probability of 1, 2, and 3. But that would get us the same answer. So if we look at the Wikipedia page for this, wiki geometric PMF. So there are 2 different versions of these formulas, and maybe I'll just grab this and blow it up a little bit. So we've got the version where it's k trials, so up until and including the first success, right? So success on the first trial, success on the second, success on the third. And we also have the version where we say how k represents the failures. So k trials or k failures. And if we have 0 failures, then our success is effectively on the first trial, right? So that's why these two are equivalent. It's a little bit of a confusing thing. You know, generally people will pick one or the other. You know, we have 2 different PMFs as a result, but they both work in the same way, the exact same way. Okay, so let's look at, it was challenge 6, I believe. Challenge 6, okay. Write a function called multiply. Given 2 numbers, multiply returns their product. It should not use the multiply operator. Okay. All right, so just snag this. So we can't use the multiply operator. 4 times 7, right? So the way that we can think about this is we can just make an accumulator, right? And we can say for num in range, and we just want to do this 4 times or 7 times, either way. Sorry, num 1 times, right? If it's 4, then we're going to loop 4 times. And we can say the accumulator is going to be incremented by num 2, right? So this is literally going to run num 1 times, and so num 1 times num 2 is going to get accumulated. And then we should just be able to return the accumulator here. And if I run this, print multiply, and we'll do 4, 7, then we get 28. So I'm assuming that's good. We don't actually need num here. I can just put an underscore. It's a little bit better Pythonically. And that doesn't account for negatives. Ooh, do we have to account for negatives? Let's see. That's a really good point. And if we need to account for negatives, we'll figure that out. Apparently we don't need to account for negatives. If we did, if we did, we could do something similar. Yeah, the instructions don't say whether or not we need to account for negatives, but let's rewrite this so it does. Let's say if num1 is less than 0, let's say negatives, we'll start negatives at 0, right? And if num1 is less than 0, then negatives, this would be just a boneheaded way to do this. If num2 is less than 0, then negatives is going to get 1 again. And then if negatives equals 1, then accum times gets -1. So this should account for negatives now. Let's just test it. -4, 7. Oh, what happened? Oh, right. I have to change something here. I'm going to say num1 gets the absolute value of num1, and I'll just change this to num1 underscore and num2 underscore, and I'll just do this also for num2. And then instead of iterating over num1, we'll iterate over num1 underscore, and we'll increment by num2 underscore. So now we get -28. And if I multiply a negative by a negative, we should get a positive, right? We get 28. If I multiply 4 times -7, we should get -28 again. So this is not the cleanest code. Like, we could probably condense this quite a bit, but this is the logic that I would use offhand to avoid using the multiplication operator. So yeah, that would be a way to do it. We're not actually testing for that in this problem though. Cool. All right. How do I get out of my while loop? Docstrings challenge 3. Let's take a look at that. The importance of docstrings challenge 3. Complete the function to the docstring specifications. All right, let's take a look at this. Oop. Just copied empty space. 1 second. And maybe I'll make that a little smaller. The Collats Calculator. This function calculates the Collats conjecture. From a starting value, this function should have a number if it is even. If it is odd, it should multiply that number by 3 and add 1 to it. This process should repeat until the number is 1. This is the starting value, where to begin. Okay, the initial value. Okay. The data tuple, this tuple should contain the start value, the largest number reached in calculation, and the number of iterations it took to reach the value of 1. Okay. So that's a 3-part tuple. The start value, largest number, and number of iterations. All right. So that kind of tells you something of what we need, right? So we have the initial value, and what we're going to do from a starting value, this function should have a number if it is even. Okay. So what I'm going to do is just make a copy of the initial value. So this is init val, and I'm just going to do, I'll just do underscore, and that'll just get the initial val. So that way we're not modifying the parameter. And the question is, how do I get out of my while loop? So why don't I just snag your code and paste it in, and we'll see. Let's see what's going on here. Okay. The list final num gets initial value. Oh, okay. That's a nice copy name. While final num not equal to 1. If final num modulo 2 equals 0, we have the number. Okay. List.append the final num. Okay. So I'm assuming this is how you're getting your iterations, your number of iterations. Elif final num modulo 2 equals 1 if the number is odd. Then final num gets final num times 3 plus 1. Okay. List.append final num. Okay. List gets the sorted of the list. Wait. Oh, okay. You're sorting it in order to get the largest value in the list. So let's take a look at final num and what's happening here. So I'm gonna do final num. I'll just print it out. And I'm also going to make an exit condition. So I'll just sometimes make something called break at, and I'll do 20. And then I'll say break at minus gets 1. It's whenever you make a while loop, just offhand, you could make an exit condition that will throw it, just to avoid running a while loop and having to kill your terminal. Not that that's a big deal to kill your terminal, just to avoid it. So if break at is less than or equal to 0, then we're going to break the loop. So let's see what we get when we run this. Oh, nothing. Because I didn't call it, which obviously I should do. Okay. All right, so we'll print this with an initial value of, let's do 20. And see what this does. Okay, so that worked with 20. 10, 5, 16, 8, 4, 2, 1. Let's do it with 200. Okay, so that completed as well. I'm not sure. I wonder what's happening in your code. I'm going to just try pasting this in and seeing if it works as expected on learn. I'm assuming the issue is somewhere here. Oh, interesting. This is giving... Okay, this is saying that the number of oh, that's why. Okay, it's because I've got the break in there. Let's try that again. Okay, it looks like that. It looks like that worked. So I think your code is fine, actually. I don't see anything else that there's nothing else in here that stands out to me. This works. I mean, maybe the only thing I would do is simplify this, but you don't have to. Change that elif to an else, because if it's not even, it's odd. I like that you did this list sorted. That's like a really convenient way to grab not only the highest number, but the you know, you can just grab the iterations from the length of the list. That's totally fine. Yeah, maybe it was just timing out. Sometimes while loops. This is the thing about Python, and sometimes while loops on our platform will time out the runtime. That's something that I've seen before, but that's not to say that. Well, that's not to say that the while loop is ineffective. If you're encountering that, you can do something like you can change your while loop to a for loop, and then have take the exit condition and make a break statement out of that. And maybe I'll just demonstrate that. Like if you run into this issue, this is actually something that this is often the way I write while loops anyway. So if the final num is not equal to 1, how about we say is equal to 1, then we break. And I'm just going to say for whatever in range, and we'll just do 1,000. And this should work. I think I wrote this right. And this should work. Yeah, this just gets us the same thing. Yeah, while loops can just be a little bit strange in terms of the resources they consume, and sometimes they just take they take longer to run than you would expect. Yeah, so let me see. That ran in essentially 0 seconds. Let's see about the while loop. If the while loop has a higher, well, you know, they both neither of them are registering in the length of time that they ran. So it may have just been something messing up on learn. Okay. Oh, you know what? That's interesting. Should multiply negative numbers. It's strange because the tests worked. That's interesting. Okay. Okay, cool. So let's kind of continue where we left off last time. Let's just look at break, continue, pass as means to exit loops. And you know, it's kind of nice. We just looked at an example of doing that with a while loop. You know, I like to, if I write a while loop, I like to set it up so it has an exit condition no matter what. That's just my tendency. It doesn't really, you don't really have to do that, you know, but when you're just writing code, sometimes you don't notice when you have a while loop that is going to run infinitely. But yeah, let's just look at these. You can break out of a for loop, you can break out of a while loop. And so for whatever in range, why don't we do, let's just make a counter, and we'll say for whatever in range 2000, and we'll say we'll just print something. We'll print this is the iteration, and I'm just going to put in, actually, why don't I'll use the counter here. I could have used an index here, but I'll just do the counter. Or let's say this is iteration number, because I don't want to have to make a condition for, you know, saying first, second, third, fourth, fifth, any of those. So this is iteration counter, and I'll do counter plus 1. Oops, counter plus 1. And let's say we just want to get out of this before, like at loop 80. So I'm going to say if counter is greater than or equal to 80, then let's just break. And then after all this is done, let's just print the counter. Oh, I did not increment the counter, so counter plus gets 1. And notice we just have iterations 1 through 80, and then counter is 80 at the end of it. That's kind of a dummy example, but there can be a number of reasons to use break. Like, there's an example in here of an isPrime function. Now, you don't have to use break in an isPrime function. You don't actually have to, but you might as well, right? Because you're going to end up running your code less. Like, you're going to have less iterations. So, prime is true. Here are a couple ways that we can say prime is false. And we can say for I in range 2 to whatever this number is, we could do, we could make this a smaller number actually. But what we can say is if at some point this number is divisible, then we can decide that prime is false, right? And we don't need to check any other numbers. So if a number is divisible by 2, we don't actually need to run this for loop so many times. Like let's say, let's make a counter. We'll start that counter at 1 this time, and we'll increment the counter. So counter plus gets 1, and then at the end of this, actually, let's put the counter up here. Yeah, let's do that. We'll just do it up here. And then we'll print ran counter times. And so let's do 128, right? So print is prime of 128. So this only ran 2 times. And if you think about that, on the first check, it's going to say, it actually only ran 1 time. Let's do that. Yeah, let's do that. This isn't going to be exactly right every time, but just, so it ran 1 time. And that's nice because we don't need to run more than 1 time, right? We can see that this is odd. We can see that this is even numbers in general, aside from the number 2, are not prime. And so we can just use break as an escape here from the for loop and running it a whole bunch of times. Let's say you're trying to figure out primeness across a massive amount of numbers. Well, that's going to be helpful because it's just going to reduce your computations. There's no reason to check every number up until n also. All right. So, in terms of while loops, like I said before, you probably just want to break out of while loops. Make sure that you break out of a while loop. So let's write kind of a silly function and say, let's import from random import choice, and let's make a while loop where let's make a counter. Let's make something called break at. How about that? And we'll break at let's break at 30, and let's say while trying to think of let's say just while true. And let's also make a collector. Let's make 2 things. let's make, yeah, let's make something called choices. And this is going to get a range of numbers from 0 to 100. And we're going to cast that to a list. And we're going to, from within here, say if the, let's get a choice. So let's get some number, which is going to get a choice from choices. And if that number is equal to 27, then we're going to break, okay? So you might be thinking offhand, well, 27 out of 100, that might take more than 30 choices, right? 30 times trying to choose it. So let's just make another thing called iterations and set iterations to, well, we'll set it to 1. And we're going to increment iterations here. And then we're going to make an exit condition, right? So if break at is less than 1 or less than or equal to 0, then we can break also. And down here, I'm going to just print our iterations. And this is kind of asking, well, how many times does it take to actually get 27? And our break at here is sort of a safety clause. And the safety clause is a little bit too low if you think about it, because one number out of 100, well, we would expect, I think we would expect to get on average, take about 100 draws. But we're probably going to see iterations at 30 a lot of these times. 58. Oh, wait a minute. I didn't decrement break at, so why don't I do that? So I'll do that here. Break at minus gets 1, 31, 31, 31, 31, and 12, right? Ultimately we get 12. So this is a safety exit condition where I'm using break, and I don't actually need this. Because there's an assumption that eventually we're going to draw the number 27. 31, oh, wait a minute. I didn't save it. So why don't we 128, 115, 43, 22, 76, 108, 296, right? Theoretically, if this was a purely random event, there would be a case where, not a pseudo-random event, but a purely random event, there would be a case where we never get 27 for an infinite number of times. Although that's super, super unlikely. But here's an exit condition for when we achieve our goal. This is a safety exit condition. When you write a while loop, it's often just a good practice to write a safety condition of some kind. I almost always do that, depending on the problem I'm trying to solve. If it's a fairly complex thing that I'm writing, I'll always do this. Write a safety condition. Okay. So that's break. And we just have some, a couple functions that do similar things to what we just did. Good question. The question is, why is it producing choices out of my choices range? It's not, actually. So num is, yeah, that's the number of iterations. And so the reason I'm capturing iterations here is, I could make this into an analysis, right? I could build a dictionary, and I could see how many times each of these numbers of iterations occurs across, like, say, 10,000 samples or something like that. And I could, determine if the average of that is around 100 or not. And I'd imagine it would be about around 100. It should be floating around 100. So if you want to skip a loop, you can use the continue statement. And let's do something like for whatever in range, let's do 100, and let's do this from random import choice again. And this is going to be this will be a little dumb, but let's do pets, and let's do cat, dog, iguana, and snake. And let's say somebody's not an iguana person. Oh, this is a little silly, but well, I'll just do this. It'll be fine. I'll just finish this out. Okay, so somebody wants to get some pets, and they're like, I'm gonna get 100 pets, but I don't want to get any dogs. So I'll call this potential pets, and call this pets. Make it an empty list, so we're just going to collect into it. I'm going to say if, well, let's call this pet chosen, and say this is going to get the choice from potential pets. So it's going to choose one of these 4 things, and if pet chosen is dog, then we can continue. And everything after this continue in the for loop will not run. And I'll say, pets.append the pet chosen. And so anything we build here should not have dog in it. Obviously, there are other ways to do this where you don't use continue, and in a lot of cases you can avoid using continue. Break ends up being quite a bit more helpful. Notice that in this list that we collected, we didn't collect any dogs, so we'd expect there to be about 70 pets in here. Just pointing this out. And if I run this over and again, 76, 80, 72, 64, it should float right around 75, right? Because a quarter of the choices here are dog. The example here is another, it's another example where we don't necessarily need to use continue. We could, I just want to point this out. We're only appending non-squares. Yeah, we're only appending non-squares here. And we're saying if the square of the number is true, if the number is a square, then we continue. We could just change this, and we could say if this is false, then we can just append the number to not squares. So in most cases, when you use continue, there's a way you can write it without continue, and it's a little nicer to avoid using continue unless there's a very specific reason you want to. And then in terms of pass, often when you'll use pass, it's when you define a function. So if you want to define a function, but you don't have anything to put in there yet, you're going to come back to it. You're maybe building a scaffold. Notice that this says there's an end of file issue when running this. And I'm going to get the same thing even if I add spaces, right? It's going to be the same problem. So I can just write pass here, and I can come back to it later. You can do the same thing with an if statement. If some condition, well, you're going to come back and fill this in. You can just put a pass in there, and that's fine. You could also do an empty print statement. What is my error here? Oh, it's because some condition doesn't exist. Let's just say if true, you know. But this allows you to write, a way to think about it is it allows you to write a scaffold for your code without filling in the logic, or you can write a bunch of functions without filling them in, and that can be very handy when you're writing code. So this is how I use pass. It's not the only way to use pass, but it's the primary way that I do. And you can think about these as, like in this case, this is what we might call a function stub. And you might hear somebody say, writing out stub to code. And that's when you create sort of like a bunch of functions, but you don't fill them in. And your intent is to come back and fill them in. So we've already talked kind of a lot about while loops. We've used them a few times. While loops, I tend to avoid them, and I think I've mentioned why I avoid them. There are a few reasons, but my main reason is computational. Like I find while loops in Python to have a little bit more potentially have a little more computational overhead. Doesn't mean you shouldn't use them, and it doesn't mean you should follow my example on this. I think I demonstrated a little bit ago, using a for loop that takes the place of a while loop, you just do an arbitrarily high number of iterations, and that's perfectly okay to do. It's not as common as just using a while loop, though. So in this case, I'm just going to actually, show this greatest common divisor problem, and it is the example that's in this lesson, and it's one of those functions that I think that you could afford to memorize if you are pretty new to Python, right? Like I recommend memorizing factorial, right? I recommend memorizing a couple functions like is prime if you're new to Python, because they can become templates for other functions you might write. And greatest common divisor is nice. It's one of those, in my opinion. So I'm just going to call this GCD actually, so I don't have to write it a bunch of times. And we're going to put num1 and num2, and this is a pretty easy function to think about. So it's kind of appropriate for a while loop because you don't know exactly how many times you're going to run it. And in this case, let's see, while num2 does not equal 0, this is the basic GCD algorithm. I'm just going to increment this, that's our counter, num1, num2, and this is, I'll do this in 2 lines. So num1 is actually, num1 is going to get, well, it's easier to do this in 1 line, actually, because we need a temp variable. So I'm gonna make a temp variable, and it's gonna get num1. Then num1 is gonna get modified. Num1 is gonna get num2, and num2 is going to get num1. Sorry, temp modulo num2. And if we were to do, we might do this by hand really quick just to show the logic here. But let's do an f string, and we'll call this runs, and then do that. And at the end of all this, we just return num1. So let's print the GCD of, oh, I don't know, 120 and 180, and see what we get. Oh, line 4, while num2 does not equal 0. getting that. Okay, local variable num2 reference before assignment. Oh, underscores. So in this case, notice I am modifying the parameter, and I'll rewrite this to not do that. But this is one of those functions. These are scalars anyway. You're probably not losing anything by modifying them, but it's kind of a better practice to not modify them. So maybe I will change these back to num1 and num2, and I'm going to say num1, num2, right? So these are copies, and I'm just going to modify them like that. So this should still work, right? Yeah, so in our example here, we are modifying the parameters, but for scalar types, that's not really so taboo. It's a little taboo for collection types, lists, strings, tuples, etc., dictionaries, sets. It's generally better to make a copy and then return that copy. So what is there anything else about this? You know, this is a somewhat open-ended problem, but you could use a for loop here, right? You could just decide an arbitrary value for the for loop, or you could take the max number, right? And that's the max of your for loop, and then you could do a break. So you could rewrite this to be for whatever in max of num1, num2. So whichever number is larger, well, that's silly. Min. You could just do the min. So whichever number is smaller, the greatest common divisor can't be larger than that number. And this needs to be range, and we probably want to add 1 to this so that we're including the minimum number. And what I can do here is say whatever that prior, what is that condition, if num2 equals 0, then we break, right? So that gets us back to break. And this, you know, so it's not that you can't use a for loop here. It's just while loops, you know, it'll take just a little bit less code because of this condition. And of course you get the same answer. We already talked a little bit about infinite while loops, and you know, just print this. Actually, while true prints eternity. And this is just running, right? This is just running and running and running. If I want to break out of it, I can do Control C, and that will break that loop. But that would just sit and run in my terminal indefinitely. So, you know, I think I already demonstrated the break at concept, and that's just creating an arbitrary exit condition in order to avoid infinite while loops. Now, it's interesting, there are some times where you do this while true kind of idea that we're seeing here. And that's for some kind of runtime where you just expect like a listener or something. If you have a port that's listening, you might check that port every some number of milliseconds, and you just have an infinite loop that's sitting there checking it. So it's not that you never want to use an infinite while loop. It's just in general, you're not going to want to. So coming up with some exit condition is a good idea. We already kind of demonstrated using a conditional check with a while loop. And this is, while x is less than 100, then we can increment x. And we'll just we'll just set x to 0. This should only run 50 times, right? And this is the condition here. So while this can be a conditional statement, it can be fairly complex. It can be, while true. Of course, if you were to write while false, that would just never run. Yeah, maybe that goes without saying, but often, I would say generally you're going to use a condition in your while loop instead of using while true. While true requires that you write a separate exit condition, whereas the condition here will just exit if you write it correctly. And we kind of touched on this concept of an open-ended problem. It's, I think the instance we used before was drawing from, we don't know how many times we're going to draw from a random number in order to get a random range in order to get a specific number. That would be an example of this. There's an example I wrote on prime windows where I think I used for loops, but I could have used while loops. Like, we don't know offhand how wide a window for a prime between primes is going to be, right? Like, we get to this prime, and then we've got a number of numbers before we get to the next prime, and we can make a distribution of those. And we can think about that, we can analyze it, but we don't know how many. We can't definitively say how far we're going to travel until we get to the next prime number. That's something that, we can analyze. We can analyze a distribution of that. And we can analyze distributions within ranges, but we don't know how far that's going to be offhand. So that would be an example of an open-ended problem. There's a concept of convergence, right? Where you, let's say, in gradient descent or in some algorithm where you've got some kind of hills and valleys, right? You drop randomly into those areas in order to start looking for a descent to a minimum, let's say, a minimum geometrically. And those problems tend to be open-ended. You don't know how many iterations it's going to take. And when you get into neural nets, you're going to see that, right? There's going to be a point of convergence where you're close enough to an answer and you just want to stop iterating when you get there. So those are all cases where while loops are going to be helpful. In general, though, you can find a way to use a for loop if you have a good idea of how long it, quote unquote, should take. You just use a for loop and add more iterations to it. Writing a menu. This is one of those things where while loops make sense, right? So, yeah, thinking about this, if you are using an online ordering form, you might be encountering a while loop. It's going to keep asking you to input things until you are done inputting things. Theoretically, you could sit there and do it infinitely, right? You could do that for the rest of your life and, have this massive order. Of course, it wouldn't let you do that. At some point, it's probably going to kick you off or reach a maximum amount. But in general, menus are good candidates for while loops. So why don't we just look at this example code? We don't ask you to write menus generally. we can, just think of this idea, right? And we don't have to get into it too deeply. I think there might be a challenge here to have you write a menu. Nope, we don't have a challenge to have you write a menu. But we just want you to know that you can use while loops to build menus. And in this case, somebody's making a selection. They're selecting 1, 2, 3, or 4 for these different items. And we have a little safety check to make sure that the input is in the selection. And then we print the selection. Oh, sorry. We append 2 selections down here. Hopefully. Yep. Selections.append. And we ask if they would like to place another order. And if they do, then we continue. Otherwise, we set another order to false, which gets us out of our while loop. So why don't I just run this? I'm going to get some bread, and I would like to make another order, and I'll get more bread. Maybe I'll get even more bread, and then I'll get some butter, and I'll get more bread, and I'm done at that point. And my order list is 1, 1, 1, 2, 1. So I can go up here and reference it. We could have written this in a way where you actually get these values, maybe with a dictionary or parallel lists or something like that. But either way we look at this, this is just, we can order as many things as we want. And that is a common use for a while loop. And then, this question is the important question. When do you choose a while loop? When do you choose a for loop? And I would just say you're almost always going to choose a for loop. If you choose a while loop, make sure it's for an open-ended problem or a menu. But anytime you know or can figure out how many iterations or roughly how many iterations you need, you can use a for loop. And you should just defer to that because it's computationally a little bit better. Cool. So let's get into strings. And strings are, they're sort of like lists. They are really, really good data structures. Python is really good with strings, right? It's great at manipulating text. It's great at traversing text. And that's one of the main reasons it's a common language in natural language processing. So, a string, something to think about with strings. I'm going to call this string, and I'm going to say this is a string. And one thing to think about here is that strings are immutable. They're like scalar types. They're considered scalar types. So when you write this is a string, let's print the ID of this. Let's print the ID of the string, and let's change it. Let's say string is going to get added on to the end of it, an exclamation point, and then let's print the ID of the string again. Notice these have different IDs. They have different IDs because they're different objects. We modified the string, we changed it. But strings, you can also iterate on strings, and that's kind of that's different, right? That's a different thing that we're doing at that point. So let's iterate on this string. Let's say for letter in string, if the letter is let's say if the letter is not equal to A, then well, let's make a new string, and we'll say new string is going to plus get the letter. So notice what we're doing here. We're collecting letters into a new string. And keep in mind that this is destroying new string every time, but it's taking its contents and putting another letter on the end of it. So if I print the new string, we should see something that is like this but has no A's in it. This is space 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 string. Okay, that's easy enough. Now, strings, even though you can iterate over them, you can also kind of split them out into lists of strings, and we're going to get into that in a little bit. So basic string operators, I just showed you one. This plus gets, right? This is just the normal incrementation operator. It's the concatenation operator with a string. And often when you see this, you could see, well, let's say we've got string 1 and we've got string 2. And I'll just say strings are cool. And I can simply add these together, right? And if I print this out, string, oh, whoops. This is actually going to be string and string 2. This is a string. Strings are cool. We could also make string 3 and, you know, concatenate these into string 3. And that works in the same way. So string 1, string 2, those added together, concatenated together, actually, can give us something in string 3. So that's a simple operator. Another operator we can use, and this comes in handy from time to time. Sometimes you want to repeat something in a string. So let's say string 3 is going to get string times 5. And let's see how that does. Oh, well, I probably want to print it out. Let's print out string 3. And notice it just concatenates them over and over again. So it just repeats it 5 times. That's a handy thing. We can also do that with lists, right? We can take items in a list and we can repeat them 5 times. In fact, or however many times. Now we've got string 3 is actually a list. Let's call this list. And if we print this out, it's going to give us this list that has this is a string, this is a string, this is a string, this is a string, etc. So in this way, here's another example where strings are kind of list-like, right? We say that they're list-like. And, you know, that's just this simple operator, this multiplication operator that does that. So concatenation will put 2 strings on, you know, next to each other. Multiplication, you know, is just the repeating operator, and we can use that for lists or for strings. So what are some properties of strings? Well, they're sequences, as we saw. We can iterate over them, and we can't do that with scalar types in general, but we can do that with the string scalar type. We can also, here's a good thing to know. If you want to get a list of the letters in a string, you can just cast the string to a list. It'll take each character and it will put it into a different slot in the list in order. So we get something like this down here. It's not super easy to see that, but notice we have this list. This space is space a string. There are times where you might want to do this. Sometimes it's easier to approach manipulating strings if they're in a list form. And you know, we'll see that. You can also check for certain letters in strings. So S in, actually let's do exclamation point in string. So actually, let's print that. Print exclamation point in string. And let's do the same thing for string 2. Oop. So there's no exclamation point in string. Oh, whoops. But there is in string 2. And so you can construct Boolean statements. If exclamation point in string 2, well, print there's an exclamation point. Notice here I'm using the backslash character to escape out this apostrophe, because the apostrophe is the same as the single quote character. So you know, you could do double quotes on this instead, and then you wouldn't need the escape character there for the apostrophe. But you know, I almost always, if I can help it, use single quotes. Every once in a while I'll use double quotes, but almost across the board I'll use single quotes. And I do that because I do that, if I need to use an apostrophe, I'll backslash and escape it. Let's see. String slicing. So this is pretty straightforward. This is just like lists. You can make a slice of the string, let's say up until the 5th character, not including it. So that should go 0, 1, 2, 3, 4, 5. So we should get this space from that. And we do. We can't see the space here unless I mouse over it, but that's how that works. And same thing, we can go, let's say 1 to 13. And we can travel by 2. And notice we start at the index 1 and we go to space. Let's see. ISA. Oh, index 2, that's why. I. And then we go 1, 2, space, 1, 2, S, 1, 2, A, etc. And we go to the 13th character. So that's just like lists, right? Like we could cast the string to a list and do the same thing, and we would we wouldn't get the same output necessarily. We would get a list output when we did that, but notice it's the same syntax, which is nice. That's a really convenient thing. So I think we cast. Yeah, we cast strings to. Well, let's think about casting a little bit more. So we can do something like this. We can say integer of 2, and this will work. And that will actually be the integer 2, but we cannot do integer of cat and expect anything reasonable to come of that, because cat is not a number. So Python will automatically check, right? Like if you have the number 5, it'll automatically check to see if it can cast that to an integer. And something that you think you might be able to do, which you cannot do, you cannot cast all the items in a list to strings by using string like this, okay? This should be str, not string. So all this is doing is it's giving us a string of the list. It's no longer a list. And that's generally not going to be helpful. If we have a list and we want to cast all the characters in it to a string, we have to jump through a hoop here. So this is going to be, I'm just going to call this list, and I'm going to say for element in list, and I'm going to make a new list. New list dot append the string version of that element, and now we should have a list that has all strings in it, and we do. So string of 1, 2, 3, 4, 5, 6. That's something that you're going to use quite a bit, and it's the kind of thing that lends itself really well to what's called a list comprehension. Not saying that you have to do this, but this is just another form of a for loop, and it's a little nicer. So for each element, I'm going to say string of EL for EL in list. And so that's just a simple list comprehension. And if I print new list, we'll see that that works. Notice 1, 2, 3, 4, 5, 6. This little code snippet on line 2, it's really helpful. You'll use this kind of thing quite a bit for casting. Now, what if you want to take all the elements in a list and turn those into a string? Like, what if I wanted a string of just 1, 2, 3, 4, 5, 6? So I can do that using the .join method on a list. And I can print that like so. And now we have a string of a list. So that's helpful, right? This is something, if you manipulate things into lists and you want to join them back together, this is going to be really helpful. So yeah, the next lesson is on join. And let me just check something here. There's a fairly challenging challenge at the end of this, and it was broken, and now it is not. So we're talking split and join here. Why don't I modify this to a string? I'll say this is a string I want to split. And let's make a split string. And I'm going to split on the spaces here. So I can say string dot split. And if I just put this space here, then split string will be a list of words. This is a string I want to split. And if I want to make this a string again, a whole string, I can do split string, and I can join it on spaces. So notice this is a space dot join, and I pass into join the split string, and it's whole again. You know, if I wanted to put some other character in there, I could do dash or dash dash, let's say, and this dash dash is dash dash a dash dash string, etc. This could really be anything, like this cat, and so now I'll get this cat is cat, a cat, string cat, I cat, etc. Notice it doesn't add it on to the end or the beginning. It just joins on it, right? So it becomes the separation character. This character here becomes the separation character. I think that's it for this kind of intro to strings. So that's all of intro Python. So let's move on to intermediate Python. Okay. Again, for intermediate Python, there's this self-placement challenge. I'm not going to go through these. These are for you. In general, these will tell you what units you can skip if you're coming in with some Python knowledge. And yeah, there's what? There's about 23 problems here. Is that right? Yeah. Okay. So we're continuing on with strings. And there's a little bit of review here. We already looked at this once. The list function. Let's just look at it again. Let's say you have a string. If you want to turn that string into a list of letters, then you use list of string, right? And say list of letters is going to get list of string. And I'll just print that list of letters. And notice that's all it is. It's a list of letters. We can join this directly. .join that list of letters, and this will make it whole again. And now it's a string again. We just talked about split, and yeah, it's pretty straightforward. So for split, it's just this. If we want to split on, let's say, the letter A, split on A, then again, we make this split. This is not a list of letters anymore. This is a list split on A. And notice what we get out of this is a joined back together thing where we've split on A. Why don't we take a look at the list itself? So print will we'll just get that. This is a string. This is, and then space string IW want to split. So notice in this list we get three things. You know, we could split on just anything here, really. We could split on R, and that should get us two things because there's only one R in here. So notice the A's are not included. They're discarded when we make that split. There are a number of sort of convenience functions in Python. We can uppercase things. We can say string.upper, and let's take a look at how that is. It uppercases all the letters, right? So, you know, a similar thing is, let's say we uppercase everything. This is string upper. It's going to get string.upper. We can string lower the upper. So that's just going to be string upper, and then we can run this lower method on it. And this is just going to give us our original string, right? So string lower, and yeah, these are just convenience methods. They there's a lot of these in Python. So upper, lower. I think .capitalize is another one to consider. So I'm just going to print this .capitalize, and this will capitalize the first word of, well, the first letter of the entire string. It won't capitalize every letter, or sorry, every word. If you wanted to do something like that, you might say, you know, word.capitalize for word in string lower. And this is another comprehension. So I'll just put this into string words capitalized. And I'll print that. Oh. I should split this on the spaces. That's why. So this is a string I want to capitalize. Now, if I want to make this a string again, of course, I have to do this join, and I'll just go ahead and do that. And now each word in this is capitalized. This is a string I want to split. So that just works the way that we'd think it would work. If I wanted to break this out into a for loop, that's easy enough too. So I'll go ahead and comment this out and start with I'll just split this first. I'll just say string lower dot split, and then I'll say for word in maybe I'll do this idx word in string words capitalized in enumerate string words capitalized string words capitalized sub idx is just going to get the word dot capitalize, and then I should just be able to print that and it'll be the same. This is a string I want to split. Each word is capitalized. Notice that this line 9 is just a lot nicer and a lot less space taken up, right, than all of that. So, you know, comprehensions are nice. That's kind of the story. But yeah, you don't have to use them. You can write any comprehension equivalently with a for loop. Comprehensions are a lot more efficient though. And they are easier to read sometimes, especially when you're used to them. So there's this replace method, and it works pretty simply. You want to do string.replace of, let's say, we're going to replace that with R. And let's just print that. Now, this method is a little strange in a way. So notice what we got. Thar are a string I want to split because it replaced is, and also, it replaced the is in this and replaced is, which may not be the behavior you want, right? You know, if we wanted to only replace that space is, then we could look for that. So this should only replace the word is, unless, you know, we have a name like Isabel in there or something, and then we might even go so far as doing this. So this should only replace this R, right? This R a string I want to split. Now, if you want to take this, what makes this method a little strange is that we're not modifying it in place, and this is probably going to get you caught up at some point. So let's print the string after we've run this method on it. A lot of methods will modify things in place, but this one does not. So if you want to save this to a variable, you actually have to explicitly do it as I'm doing here. So string gets string.replace is R, and then we get a permanently modified variable there. So another thing we might do here is count the number of letters, like say the number of S's in here. So let's count the number of S's. It turns out there's 3. So 1, 2, 3. Oh, well, wait a minute. Oh, that's because I replaced R. Why don't I get rid of that? So now we have 4. 1, 2, 3, and 4. So now what if you only wanted to replace a couple of S's in here? So you can start by replacing the first S like this. Let's change S's to R's and see what we get. Oops. Need to print the string. There are a string. I want to replit. So if we only want to replace the first one, we could do this. We could just pass in how many we want to replace. And notice we only replace the first instance when we do that. If I put 99 in here, let's see what happens. It replaces all of them. So you don't have to guard for the upper end of this, right? You can say, well, I want to replace as many as this, but maybe I don't want to replace more than that. Yeah, if you just want to replace the first instance, this works. To just put in 1. There is also this idea of chaining methods, and this will work for some methods and not other methods. So, you know, maybe what we want to do is capitalize before we replace anything. And if we do that, capitalize, not capitalize. Notice we just capitalized the first word first. So you can use these two together, but you can't always trust your methods to be able to be chained like this. This looks a lot like JavaScript, and this tends to work for string modification methods. It doesn't work for some other methods where you might expect it to work. Yeah. Okay. And so this kind of brings us, well, this brings us to string formatting. I do a lot of string formatting when I'm working on these, and I think that it's a good thing to just know how to do, right? It's something that you're going to probably do a lot, and there are a few ways to do this. So let's make variable called cat, as always. Let's make another one. Let's call this cats. And let's make something called numcats, and let's say that's 32. And let's say dogs. And let's say numdogs gets 23. And you can just do this. You can say I have plus this string cats, right? And actually, let's do plus num cats plus space plus cats, and I have plus num dogs plus dogs, actually plus space Notice how kind of tedious this is. And when I run it, well, I have an error because it's kind of tedious. It's hard for me to see these plus signs and things. And also notice this, I can only concatenate string, not int to string. So number of cats, I actually have to cast this to a string in order for this to work correctly. And I'll cast num dogs to a string. And notice that works. I have 32 cats and I have 23 dogs. What would be a lot nicer is if I just did something like this. I have and I have curly bracket, and this is called an F string. I can just put an F in front of this. This is the best way, I think, to interpolate values in Python. I think this works really well, and we're just gonna have num cats. Obviously, we could just put the string cats in there and that'd be fine. Num dogs. And that both of these work, and they are equivalent to each other. Now, we could do another method in here called .format. In general, I like F strings where we have this little F that precedes everything. I like F strings more. But I used to use .format all the time, and it's just this. You put the .format method on here, and then you can do num cats, separated by commas, num dogs, and this will work in the same way. Right? There's nothing really different about these. They're all pretty equivalent to each other. But F strings are sort of obviously nicer in a way. It gives you something that's readable in line with itself, right? Like I have num cats, and I have num dogs. Makes sense. There are some other small aspects of using .format and using F strings. Namely, the one that I just want to point out to you is division, right? So I'm going to use the same example that we have here, essentially. So 10 divided by 3 is going to give you 0.3 repeating, 0.3 repeating, 3.3 repeating. So let's just look at that. 10 divided by, well, x divided by y. And we get 3.3 repeating. In statistics, a lot of the time, you're going to find that something becomes less meaningful, right? Something becomes less meaningful. The more values you are to the right. It's like you can't be sure about the probability of something, like 0.017999999. Computationally, those nines way off to the right stop meaning anything. And in those cases, you want to limit yourself to a certain number of values. So what I would do here is, make this an F string, and we can simply we could do this with an F string, but I'm going to do it with .format. I think it's a little nicer to think about it this way. So we'll do .format, and then we'll pass in x divided by 3. And so this is just going to give us the answer to 2 decimal places. Oh, wait a minute. Why is that? Oh, that's why. 0.2 F. There we go. So 3.33. 5 decimal places. We can do this. 3.33333. Something to consider is this doesn't just drop the number, it does round. So if you're trying not to round, that isn't exactly going to work in this case. But there are a lot of different kind of string interpolation settings. I think this is the most important, just the number of decimal places when you do division. So 3 decimal places is just this, colon 0.3 f. F here is indicating float. And yeah, I think that's good for that. So I'm gonna leave tuples for another time. I'm gonna leave them for Wednesday, and let's think about some kind of problem here. Well, let me point you at this prime windows video that I did a while back. I think it's fun. Let's look at playlists. And there's an associated GitHub here. And this is just taking an analytic approach. Images. I wonder if. Oh, cool! I didn't remember doing this. This is taking an analytic approach to examining windows of prime numbers, and kind of plotting them out. So most of the code is. Oh wow, did I make video of this? I didn't even realize I did that. That's pretty funny. I was just thinking this project was exploring some code, but which it is, right? It is exploring some code. So is prime, find the next prime, then we get all the primes in a window, we get the distances, so we make distances. And then we build a primes distribution and then plot it. And I think these kinds of analytic games, like this is with some kind of number theory stuff, just prime exploration. I think that it'll give you some insight into kind of an analytic process in general, which is a lot of what you're going to be doing in the technical interview. So, this is not exactly a random process, but we can start to think of it as a random process in terms of, it's a systematized process, let's say, but, we gain some insight into the distributions of primes here. So, what are we plotting here? I don't exactly remember. I think we're just plotting the distances between primes and the occurrences of those distances. Yeah, that's exactly what's happening. And one thing that's interesting is that the most common distance between primes is 6. And I didn't know that was true. I'm sure there's some mathematicians out there who know all about this, but I was just exploring this out of my own curiosity. I was kind of wondering if this looked like any familiar distribution. And at the end of the day, I don't really think it is. I think it's a primes distribution between different windows. So this is, gives us a lot of information, the number of primes between 460,000 and 470,000, and gives us the maximum distance between primes in that range. And one of the expectations we might have is that the higher we go up, in our prime windows, the higher the maximum distance between primes we'll see. But we can't exactly answer the question, as we approach infinity, does max distance approach infinity as well? There are these other questions that we might try to ask, but we need some sort of systematized approach to doing that. And yeah, I'm just pointing this out because I think it's a pretty accessible little follow along. There's a video that I posted in the Slack channel, and this GitHub repo, all this code should work as expected. So if there aren't any questions, I might wrap up here because we're at a good stopping point in the Learn materials. And I don't want to get into tuples quite yet. Oops. Bring this back up. And yeah, so I think I'll call it there. And next time we'll, after questions or, interspersed with questions, we'll start looking at tuples. All right. Thanks so much, everybody, and have a great evening, and I will see you in class in about an hour.